let me get started. Let's take a few more questions. If anybody else wants to ask some questions. General questions. They don't have to be about this lecture.
So maybe what are the hot topics now in machine learning up to date?
Yeah, the hot topics in machine learning, that's a very good question. An interesting way of knowing what the hot topics are is to look to see what is being presented at the main conferences. So these are the 4 big conferences in machine learning, I would say, are they're NIPS, ICML, UAI, and AI Stats. Then there are obviously other related conferences like KDD for data mining, CVPR, and ICCV for computer vision. These are all the acronyms, right? There's so many acronyms in the field. And then, in robotics, there are things like RSS, etc. But let me focus on just the kind of more pure machine learning conferences, these 4 conferences. So I happen to be a program chair of NIPS this year, which is a huge amount of very painful work. But the other interesting thing about being program chair is that I can see every one of the 1,400 papers that has been submitted this year. Not the ones that are accepted, but the ones that, obviously we'll see the ones that are accepted later. But this gives insight into what the hot topics are. A lot of people are very excited about deep networks. That's one kind of interesting, very active topic. I would actually say, just looking at the distribution of the keywords of submissions, deep networks and Bayesian non-parametrics were 2 of the frequent ones. And then there are many other ones that are also very active these days. There are some hot topics like, causality is sort of interesting, and people have been working on this recently. There are topics like structured prediction. Networks, sparsity, L1, regularization, and beyond L1. These are all very, very hot topics. And then just like, many different topics in optimization. It's just a random sampling, but I could actually be more scientific about this. At some point, Max Welling and I, when we actually have the NIPS conference, we'll prepare a presentation. We'll give a distribution of like the keywords that were submitted, and then there's also always an exercise that says which keywords or words in your title were predictive of having your paper accepted and rejected, etc. And that's always a moving target. Okay. Any other questions? Yep. 2 more. Yeah. So in the back there.
Okay. So in non-Bayesian data mining, we usually use measures like DC dimension for quite the complexity of the model, and I guess you are not really interested in that here because Bayesian mechanics give you already
the complexity, yeah.
The complexity somehow. But VC dimension also gives you some guarantees that you are going to learn if you have some assumptions.
Mm-hmm.
Is there something equivalent here?
That's an excellent question. So just to repeat the question, so in classical kind of frequentist machine learning and data mining, people use measures of complexity like VC dimension, and that gives you guarantees on how well you can learn from data, and gives you bounds on generalization error performance of your method. Is there something analogous to that in the Bayesian framework? So first of all, in the Bayesian framework, we don't have to penalize models for complexity as long as we are trying to do these integrals. So all of the models I'm talking about today are infinite dimensional. They have infinitely many parameters. So it doesn't make sense to even talk about the VC dimension of these models. But because we're integrating out those infinitely many parameters, actually the models are not going to overfit because we're not fitting anything. On the other hand, and I talked about Occam's, Bayesian Occam's razor and things like that as ways of automatically penalizing models for being too complicated. But it's still useful to have these theoretical guarantees on the generalization error. And one thing that is very interesting is applying some frequentist theory to Bayesian methods. And this is a very active area of research. So I give you kind of two representative pieces of work here. One of them is something called pack Bayes. And pack Bayes is a set of frequentist theory based on the probably approximately correct framework of Valiant originally that can be used to analyze Bayesian methods. So you can give generalization error bounds on, for example, something like a Gaussian process classifier. So that's nice because you can, from my point of view, I feel like I can have my cake and eat it too, is the expression, right? So I can be a Bayesian and I can still have frequentist guarantees, which is very nice. Another set of theory here is a lot of work in Bayesian non-parametrics. So a lot of work in Bayesian non-parametrics on things like rates, consistency, something called Bernstein-von Mises theorems. Which talks about sort of convergence to Gaussianity of the posterior. These rates and consistency results are basically looking at frequentist rates of Bayesian methods. Okay, so you can compute these, and there's a lot of very elegant work in the finite dimensional parametric setting. It's very easy to do this. In the infinite dimensional non-parametric setting is much harder, and it's a very active area of research. So for example, you can say, oh, that the Gaussian process, if you adapt the bandwidth parameters, length scales, has near optimal rates for function approximation or something like that. And those rate results are classical frequentist results. So again, it's classical results apply to Bayesian methods. Okay, I'll take one more question. I think there was one there. Yeah.
I have a general question about machine learning. If you compare, for example, what was possible to do 10 years ago, 5 years ago, how could you summarize, for example, the advances? And how would be your predictions about the next 5 years?
Yeah, that's a good question. So from 5 or 10 years ago to now, I think there's a very big difference in what has happened in the field. Part of the difference is that we have a lot more problems motivated by real-world applications in industry. So 10 years ago, you know, Google and Microsoft and Facebook and so on were not really, Amazon, you know, they're not active in this sort of area very much. Microsoft was a little bit, but not any of the other ones. Now, many companies doing data analytics and internet companies and so on use machine learning. What that means for the field is that people are more and more concerned with large-scale applications. In terms of methodologies, you know, obviously people have been trying to scale up machine learning methods, but there's been a lot of new interesting developments. I would say, you know, kernel methods have matured into a very standard thing, but people have moved on to do things like structured prediction, which is a very big topic these days, and relational learning is another big topic that is quite relevant. And I think just people keep discovering new learning problems that are interesting. But also the ambitions are getting higher into kind of fully unsupervised learning, into trying to solve some problems in AI, maybe using machine learning. Deep networks are very popular, and that's grown in the last 10 years. So these are all developments in the recent past. And I don't know what's going to happen in the future. It's very hard to tell. Yeah. Sure.
Also general, because you are talking about Facebook, social media, and this industry examples. What can you say about use non-parametric base in image processing, computer vision, object tracking?
Yeah, there's certainly some use of non-parametric Bayes in computer vision. I'm not as much an expert in computer vision. I don't generally go, for example, to CVPR and ICCV, but from my understanding, there are a number of very good computer vision groups that are using Bayesian non-parametric methods to try to learn you know, object categories in an unsupervised way, some of it to do some tracking when you don't know the number of classes, etc. So there's some work, but it's not really, you know, dominant. It's kind of still a minority. Okay, let me move on. I've talked a little bit about clusters. I want to talk about hierarchies. I want to talk a little bit about time series, about sparse matrices, and about networks. Okay? And then, you know, then we'll finish in about an hour. Okay. So I'll go fairly quickly through this material. This is kind of researchy material. I don't expect you to absorb everything, but I just want to give you a flavor for some of the generalizations of these Bayesian non-parametric methods beyond the Dirichlet and Gaussian process. So one interesting way of doing generalization is by trying to model hierarchical data. So, you know, in a lot of situations, the data may have been generated from a true hierarchy. Like, for example, you know, if you look at evolutionary trees, they're basically hierarchically organized. Hierarchies are also useful for doing parameter tying in complicated models, and they're useful for visualization and interpretability. So let's look at some Bayesian non-parametric models for hierarchies. There are two nice ones that I'm going to talk about. One of them is called the Dirichlet diffusion tree. This is a very interesting generalization of a Dirichlet process mixture that gives you hierarchical structure between the components. And the description is, you know, you can sort of follow it from this slide. You could read the slide and then read the paper if you want to really understand it. I'll just show it to you through some pictures first. Okay? So the way in the Dirichlet diffusion tree that we're going to generate our thetas is not by drawing them from a Dirichlet process, but by considering some sort of diffusion in theta space. So here is the what the axis here shows is along this axis is theta, and along this axis we're going to call this time. So time goes from 0 to 1. This is just a unit of time. It's not real time. We're just going to use this time variable to be able to create a hierarchy. Okay? So it doesn't have to be for modeling time series. All we want is for our points at this fictitious time 1 to be organized somehow or clustered somehow hierarchically. So here's how we're going to do it. The first data point starts at the origin at 0, at location 0, at time 0, and then it follows Brownian motion, independent Gaussian increments, Brownian motion for unit time, and ends up here. Okay? So that's what the first data point does. Now, the second data point does the following. It follows exactly the path of the first data point up until some time, and the time is a random variable, some time where it departs from the path of the first data point and it follows its own independent path. Okay? So it's almost like, imagine you have ants, and the first ant goes somewhere, and the second ant follows the trail of the first ant, and then at some point splits off and goes in a different direction. Now, the time of this breaking off point is given by some function which in the Dirichlet diffusion tree is called the divergence or hazard function. Okay? So it's a random variable that takes on values between 0 and 1, and it splits off at that point. Okay? Now, here's the third data point. The third data point follows exactly the path of the first two data points. And again, it diverges at some point, for example, here, and then goes off independently and ends up here. The fourth data point, just as this is a sample of a draw from a Dirichlet diffusion tree, the fourth data point does the same thing. At this branch point, the fourth data point has to decide whether it follows data points 1 and 2 or data point 3. And it chooses which branch in proportion to the number of data points that have followed that branch. So with probability 2/3, it follows this path. With probability 1/3, it follows this path. In this case, it happened to follow this path. And then it branches off here. Okay? So what do we have? We've drawn 4 data points. These 4 data points are the data points at time 1. And these 4 data points are actually drawn from a hidden hierarchy. Okay? So if we were to draw many, many data points from this Dirichlet diffusion tree, the structure that we could get is something like this. These are 3 example draws from a Dirichlet diffusion tree. And it's hard to see the hierarchy here, but essentially, if you look at it a little carefully, you'll notice that there's some clustering, but the clusters are also clustered. Okay? So, let's look here. This is a particularly good example. There's a cluster here, and then there seem to be something like 3 clusters here, and then another 3 clusters here. Okay? And that's the whole point of a hierarchy. You don't have clustering, you don't have flat hat clustering, you have structure inside your clustering. Okay. So this is a very elegant model, and this has, until recently, it hasn't been applied very much in machine learning or Bayesian non-parametrics, but more recently we've been reviving this model. This is a very interesting idea of Neil's, Radford Neil from 10 years ago, right? Okay, so here is another way of generating hierarchies. Again, I'm not going to describe this in detail, but I just want to give you the pointer to it. This is an idea called Kingman's coalescent. It goes back to 1982. And it's a model that's used for modeling genealogies in areas like genetics or population genetics and things like that. And this is a way of generating hierarchies, which also involves some notion of time. But now what we're going to think about is time going backwards. So consider, everybody here, all individuals currently. If you go backwards in time, then let's take all of us here. If there are no brothers and sisters in the room right now, right? No? Maybe first cousins? Any first cousins here? No? But if we go back enough generations, probably there'll be a point at which two people in this room will have a common ancestor, right? So then you keep going back until everybody ends up having a common ancestor. Okay? That's the way you generate your tree. So working backwards in time from time t equals 0, you generate a tree with n individuals at the leaves by merging their lineages backward in time. So the lineage is just the sort of ancestors that you have. And in the Kingman's coalescent, every pair of lineages merges independently with some rate. Without loss of generality, we set the rate to be 1. And so the time of the first merge of n individuals is given by an exponential distribution with rate roughly n squared over 2, because there are n squared over 2 pairs that could possibly merge. And then with probability 1, this generates a binary tree where all lineages are merged if you go infinitely back in time. Okay? And then this is a nice model because although I've defined this for n individuals, this model generalizes to the limit of infinitely many individuals. Okay. And it's exchangeable over individuals and has uniform marginals over tree topologies. And this model has been used for hierarchical clustering. So this is just a picture from the paper. It's too small to see. But essentially, here is a sample drawn from the Kingman's coalescent. It looks a lot like the samples from the Dirichlet diffusion tree. It's a slightly different model, though. And this gives you hierarchical clustering in your data as well. Okay? Here's another very important model in Bayesian non-parametrics called the hierarchical Dirichlet process, which is especially important when you have data that's divided into multiple groups. Okay, so imagine you have J groups, and what you want is you assume that there should be clusters within each group, but you believe that the clusters are shared between the groups. So for example, there could be, you could group the people here by their backgrounds, like what you studied, if you studied computer science or mathematics or physics or something like that. So there's some distribution over the clustering of the people here. Then we could go to another group, maybe classroom next door, and there would be a clustering of the people there. And the idea is that the cluster identities are shared between these different groups. So maybe there's some different fraction of computer scientists in the room next door, different fraction of mathematicians, etc. Okay, so the basic way that works in the hierarchical Dirichlet process is you have a Dirichlet process. You have a Dirichlet process for each group, but the base measure of that Dirichlet process is itself drawn from a Dirichlet process. So there's a little graphical model for a hierarchical Dirichlet process, and that the sharing of the base measure gives you sharing of the clusterings in the Dirichlet process. So it's, again, I'm not going to go into it in detail. I just want to give you a pointer to this. So now let's talk very quickly about time series. A very classical model for time series is the hidden Markov model. And these are widely used for many applications like speech recognition, bioinformatics, biophysics, text modeling, etc. And the basic idea behind a hidden Markov model is you have a sequence of observations, y1 through yt. T denotes time. And you assume that your observations are drawn from some hidden state sequence, S1 through ST, and that the hidden state sequence has a Markov property. So the state at some time t only depends on the state at the previous time. And moreover, your hidden states are discrete. Okay? So that's the basic definition of a hidden Markov model. So we're going to just call K the number of states in an HMM. So in the HMM, the transition matrix that defines the probability of ending up in state, in some state given the previous state, is given by a K by K matrix. And we can think of a hidden Markov model as a time-dependent mixture model, because at every point in time, we're clustering the data into one of K clusters, or mixture components, but the time dependence says that the data is not IID. The clustering actually depends on the clustering at the previous time. So this is an interesting observation, because we know that the Dirichlet process mixture is a way of defining infinite mixture models. We know that the HMM is a generalization of the Dirichlet process mixture. So an infinite HMM is just a way of defining an HMM where the number of hidden states at any point in time is potentially infinite. Okay, so K goes to infinity. And the infinite HMM, we can think of it as just being a more flexible model than the finite HMM, because we don't have to give a limit to the number of hidden states that you have. But the tricky part of the infinite HMM is that if you have K going to infinity number of hidden states at any point in time, then the transition matrix between every pair of states is given by a K by K matrix, but now in this case it's going to be an infinite by infinite matrix. Okay? And that just sounds very nasty. The good news is that the infinite HMM can be derived from a hierarchical Dirichlet process, where essentially what you think of is that each of these rows of your transition matrix are noisy versions of some common base measure. Okay? So you draw a single, draw from a Dirichlet process for your base measure over your K going to infinity number of hidden states. And then each of these is drawn from a Dirichlet process with mean given by that thing that you drew. So this is sort of a kind of a technical way of describing that. The common base measure is drawn from a Styk breaking distribution, or it could just be a Dirichlet process draw. And then the transition parameters for each of the states are drawn from that Dirichlet process with mean beta. Okay. And what that allows you to do is it allows you to have a hidden Markov model with infinitely many states, and you can also do tractable inference in this model. So here are just some examples of draws from the infinite hidden Markov model, where you can see this, the pictures. What they're supposed to represent is that these are the states. This axis is the state visited. I've just indexed the states 1, 2, 3, 4, 5. So at time 1, it's in state 1. And then it either stays in the same state or visits a new state. And this is time. So what you can see is, the longer this infinite HMM runs, the more new hidden states it visits. And this envelope grows, roughly logarithmically. Okay. This picture, incidentally, is a picture obtained by looking at a book. This is Alice's Adventures in Wonderland. These are the words, and these are the individual words that are new words that are observed. Okay. So as you read the book, more and more new words enter into the book. That's the story here. So a lot of real-world data, in particular things like text, have this property that the more of it you observe, the more new things you find in your data. Okay. And that's what a lot of these non-parametric models are trying to capture. So the infinite HMM has an interesting history. We developed it about 10 years ago. In 2005, Tay et al. Showed that they could rederive it from the hierarchical Dirichlet process. And then over the years, we've come up with some efficient ways of doing inference. So there's some open source software for it. And we have kind of parallel and distributed implementations. And at this point now, about 10 years later, we have really scalable algorithms for running infinite HMMs on big data sets. So that's quite nice because, it wasn't really that usable early on, but now it's quite usable. Here's an application of infinite HMMs to a few different things. This is change point modeling. This is video segmentation. This is a work by Tom Steepleton where he did a video segmentation of people playing on the Nintendo Wii. Okay, so you can segment, you can segment the frames of video into different motion gestures using an infinite HMM. The point of that is that you don't have to decide how many segments in advance. The algorithm will tell you how many segments it wants to use. Okay, so now let me move on to sparse matrices. You can think about clustering, as I've talked about, as being represented in terms of a sparse binary matrix like this. So on the rows, what you have are the data points, and on the columns, you have clusters. And a particular clustering of the data corresponds to an assignment of a particular 1 in each row and zeros everywhere else, right? So the Chinese restaurant process defines a distribution on partitions of the n data points, which could be represented in terms of this cluster, and a Dirichlet process is used underlying that kind of process. Now, what I want to talk to you about in the next 5 minutes or so is a different kind of model. This is called feature allocation models. So in some sense, these are generalizations of clustering, but now each data point, instead of having to belong to one and only one cluster, can have multiple features simultaneously. Okay? So in this matrix, the rows have to have only a single one on each. Each row has to have only a single one, and all the rest have to be zeros. In this matrix, you can have any pattern you want. Okay? A data point can have multiple of these features allocated to it. And The analogous thing for feature allocation to the Chinese restaurant process is something we developed called the Indian buffet process, which is kind of the name was a bit of a joke after the Chinese restaurant process, but it's now used by everybody. The underlying measure is not the Dirichlet process, but it's the beta process. Okay, but I won't talk about that in detail. So let me describe the Indian buffet process a little bit. We want distributions on these binary matrices. So here is a way of generating these distributions. So imagine you have a sparse binary matrix where an element of this matrix Znk equals 1 means that object n has feature k. So let me be clear. I'm not talking about observed features of data. I'm talking about hidden features of data. Okay? It could be observed features, but in most of the applications, we're interested in learning about some hidden features of data from some other observed things. Like, for example, in a few slides towards the end of this lecture, I'll talk about some network models. Let me just talk about that right now. Imagine we're modeling a social network, and you have different people, and you observe friendship relationships between these different people. But actually, what's happening is that people might be friends because they have common hidden features. Like, for example, two people might be friends because they come from the same hometown, or two people might be friends because they have the same hobby, or they're taking the same classes, etc. So this matrix is meant to represent people and the hidden features that they might have. And then the observable data would be whether two people are friends or not. And now, of course, it doesn't make sense to say that because you come from this town, you can't have this hobby, right? So, you can have any combination of these hidden features. You can come from this town and have this hobby. Maybe you lived in this other town. Maybe you're taking this class. Maybe you studied at this other university before. There are these many possible features that you could have. So they're not mutually exclusive. Clustering is a very limited process because it assumes that every data point can belong to only one and only one cluster, right? And I don't like clustering because of that. I think it's actually a kind of an unnatural model for many real data sets. In this kind of feature allocation model, data points can belong to multiple overlapping clusters. Okay, how are we going to generate these binary matrices? Well, here's just a very, very simple way of generating them. So Znk equals 1 means that object n has feature k. We're going to draw that from a coin toss, a Bernoulli distribution with parameter theta k. Theta k is a parameter associated with each column of this matrix, representing essentially the frequency of some particular feature. But of course, the theta k's are not known, so we put a prior distribution on the theta k's, and we're going to use a beta distribution because the beta is conjugate to the Bernoulli. So if we do that, the math all comes out to be very, very simple and very easy to work with. So if we use a beta distribution with some particular parameters, alpha over big K is the total number of columns in this matrix, comma 1. 1 can be changed afterwards if we want. Then note that under these assumptions, the probability that Znk equals 1 given alpha is simply alpha over big K divided by alpha over big K plus 1. So as the number of columns K grows larger, the matrix gets sparser and sparser. So if the matrix Z is n by big K, the expected number of non-zero elements under this simple model is going to go to n alpha. There are n rows, So on average, alpha, this parameter here, controls the number of ones in each row of the matrix. That's the expected number of features that every data point possesses. Okay? Now, even in the limit as k goes to infinity, the matrix is expected to have a finite number of non-zero entries. And the infinite limit results in what's called an Indian buffet process. So this is the analogy to Aldous' Chinese restaurant process. And this was developed when Tom Griffiths was visiting London. And he said something like, oh, many Indian restaurants offer lunchtime buffets in London with apparently an infinite number of dishes. So this is a picture of an Indian buffet restaurant. It looks like there's infinitely many dishes. I'm not sure. But here is the basic idea behind the process. We're going to generate one of these binary matrices. The way we're going to generate it is the first customer comes in, starts at the first end of the buffet, and serves himself Poisson alpha number of dishes until his plate becomes full. Okay? So that's the first customer. Now, subsequent customers, what they do is they move along the buffet. So if you're the nth customer, you move along the buffet. You sample dishes in proportion to their popularity. So it's sort of like each dish has above it a counter for how many times people have tried it before. So you serve yourself dish k with probability mk over n, where mk is the number of previous customers that serves themselves dish k. And then after you've encountered all dishes that have been tried previously, you also try a Poisson alpha over n number of new dishes. Okay? So this is the adventurous part where you're trying new dishes. Okay. So this generative process generates a binary matrix, Z, and that binary matrix is a draw from the Indian buffet process up to basically a reordering of the columns. So we've basically ordered the columns so that all the interesting stuff is happening on the left, and the whole rest of the matrix has all zeros in it. Okay? There are infinitely many dishes that so far nobody has tried in the buffet. Okay? And that's just a reordering of this matrix. Okay. So that's the Indian buffet matrix. And you can actually, the nice thing is you can actually write down an expression for the probability for any particular matrix. Don't worry about that in practice. This is quite useful if you're going to do learning in this model. And it has a number of properties. It's infinitely exchangeable. The number of ones in each row is Poisson alpha. The total expected number of ones is alpha n. The number of non-zero columns grows with alpha log n. So you can see here, this is a sort of growth. It has, like the Dirichlet process, it has a Styk breaking representation. Like the Chinese restaurant process is related to the Dirichlet process in the same way as the Indian buffet process is related to the beta process. This was shown by Thibault and Jordan. And there are more flexible generalizations. The model I've described so far has only one free parameter, alpha. And there are generalizations to 2 and 3 parameters. Okay. So here is just the big picture, another one of these cubes relating different models to each other. So we could start with finite mixture models, things like Gaussian mixtures and k-means and so on. And then we could apply different operations to that. So one of them is to take a finite parametric model and consider, following the blue arrows, an infinite non-parametric generalization of that. So the Dirichlet process mixture is an infinite generalization of finite mixture models. The orange arrows correspond to taking a static model and considering the time series generalization of that static model. So if we start from a finite mixture model, the time series generalization of that is the hidden Markov model. And then the non-parametric version of that is the infinite hidden Markov model. And similarly, we could arrive at the infinite hidden Markov model through this direction. Okay? Now, the Indian buffet process and other kind of similar models are following a green arrow, which corresponds to factorial representations. So factorial representations just refers to the fact that, just going back to this picture, we're going from a clustering model, right, where data points belong to one and only one cluster, to a feature allocation model where there are many combinations of features that could be allocated. So this is the green arrow that goes from clustering models to factorial models. You can do that for finite mixture models, but then if you do that for infinite mixture models, you get the IBP. If you consider the time series generalization of that, you get what's called the infinite factorial HMM. Okay? All right. So that's the IBP and the infinite HMM in some context here. Let me talk a little bit about inference and applications of the IBP, and then I'll move on to basically talking about things like networks. So the IBP has been used in a whole bunch of different models, and the basic idea is you have some observed data X, and you have some hidden variable Z. The Z has a binary matrix representation, and you want to do inference about these hidden things like Z and alpha given X. Okay? So again, this distinction between models and methods becomes useful. We've defined a model, and now we can consider what are the different methods that can be used to learn that model. And there are many different approaches that have been used, things like a lot of different MCMC methods, some variational methods, some expectation propagation, etc. And in terms of models, these models have been used for models of graph structures, protein complexes, collaborative filtering, sparse feature analysis, sparse PCA, overlapping clusters, etc. Here's an application to independent components analysis, if you're familiar with that. Basically, the observed data is assumed to come from some hidden factors, but we're going to assume we have ... here, so we don't know how many hidden factors we have. And we assume that there is a sparsity in this hidden factor distribution. Okay, so many of the hidden factors are 0 most of the time. Here's an application to matrix factorization. Again, I'm not going to go into the details. The idea is you have some matrix of data, genes by patients or users by movies, and you want to represent that in terms of latent feature matrices given by an IBP. Okay? So to summarize, we have probabilistic modeling and Bayesian inference, the same sort of thing. And most of this lecture I focused on non-parametric Bayesian methods. I talked about Gaussian processes for regression and classification in the previous lecture. And then in this lecture, Dirichlet processes, infinite HMMs, also some hierarchical models, and then the Indian buffet process. Good. So any questions about that? And then I'll move on to kind of networks and other topics. Any questions? This is my lecture 5 in 4 days. So it's a little bit compressed, but at least I can give you a flavor for everything I was planning to talk about. in the 5 days. Okay, so let's talk about some more advanced topics in Bayesian nonparametrics. So again, we're going to move beyond the Gaussian process and Dirichlet process. I talked a little bit about latent features and sparse matrices. Then I'll talk about networks and exchangeable arrays for relational data. Okay, so we've seen this already. Models based on the Indian buffet process. So here is again, this is very hot off the press. So this is work that was also presented at ICML last week. And this is an approximate inference method for Indian buffet processes. Okay, so in terms of deterministic inference, there are many different approaches, both MCMC and deterministic approaches that have been proposed. But the question is, how good are they? You know, which one is faster, which one is slower? You know, what use is it to propose 10 different methods if you're not going to compare them? So what we're going to talk about, what I'm going to talk about is work done with Colorado Reed, one of my students, where we proposed a new method based on submodular maximization. And then we compared it to some of these other methods for IBPs. So the approach is we're going to approximate the full integral over everything by a maximization. Now it sounds like, you know, I'm anti-maximization, but actually, you know, maximization sometimes I find very useful as long as I know that I'm approximating an integral with my maximization. So here, what we're going to do is we're going to maximize over the binary matrix Z while integrating over everything else using a variational approximation. Okay? And the interesting thing about that is that the maximization over each row of Z results in what's called a submodular maximization problem. So this is another very nice keyword that's quite popular in machine learning these days. And the idea of submodularity is a diminishing returns property for set functions. So imagine you have a function f, and this function f gives you a scalar value for sets of things. So if A is a subset of B, then if f is submodular, then adding some element to A gives you a larger gain than adding that element to B. Okay, that's the definition of submodularity. There's a very easy way of thinking about submodularity if you ever forget. Okay, think about it like this. Giving €1 to a poor person makes that person much happier than giving €1 to a millionaire. Okay? So if f is happiness, and the set that we're talking about is a set of money, then the function, the happiness as a function of money, is a submodular function. It has diminishing returns. Less and less happy the more euros you collect or whatever. Okay. Now, this submodularity is actually a very nice discrete generalization of the concept of you know, concavity and convexity, but to set functions. And similarly, if you have submodular functions and you want to maximize them, just like in convex optimization, it turns out that we can approximately maximize submodular functions with a simple greedy algorithm, and we get a 1/3 approximability guarantee. What that means is the greedy algorithm that just, you know, adds one element at a time to the set until the, you know, until this thing becomes negative, let's say, that results in a value for f that is 1/3 of the global optimum. Okay, and maybe 1/3 of the global optimum is not very good, but in general, the submodular maximization problem is intractable for set functions, for submodular set functions, but the greedy algorithm will still give you an approximation guarantee. Okay. So we can apply this kind of interesting bit of discrete optimization to Indian buffet processes. And then the pictures that are interesting to look at are pictures that look like this. So these pictures involve running a model on a fairly large data set. This is 100,000 data points. Each data point is 1,000 dimensional. Running different models for different amounts of time. Okay? So time is on this axis in hours, and performance on test data is on this axis. This is test log likelihood. Higher is better. Okay? So what do we see in a picture like this? We see that some methods, for the same model, some methods, even if you run them a very long time, their performance is not very good. Okay? Other methods very quickly give you good answers, but then they plateau. And then other methods are slower, but they end up with a higher plateau. Okay? So there are a whole bunch of interesting things about this picture here. We compared a number of different methods. This is our method. This is called the MEIBP, based on submodular maximization in orange. And at least on this data, it seems to do very, very well compared to the other methods, including some sampling methods and some variational methods compared in there. Now, this is an embarrassment here for us, because these are all IBP-based methods. This is a parametric non-negative matrix factorization model. It's a different model, but we thought for honesty purposes, we would put it on this plot to see how well it did on this data. And it incredibly quickly gets a pretty good answer. Okay? But these are all versions of non-parametric models. That's a particular parametric model on this data set. The other interesting things is that some of these approaches that have been proposed recently, at least in the implementations that we got of them, they didn't even complete one iteration of the algorithm in the 36 hours that we gave it. Okay? So just because something is you know, a more recent paper or whatever, it doesn't mean that it's going to work better for your particular algorithm. Unfortunately, you have to do these comparisons and try them out on your particular data set and method. Any questions about this? So here are some other examples. This is on a real data set. That was on a synthetic data set, which we just made to be kind of large to test these things. This is on a real data set. Again, this is the MEIBP, which does pretty well. This is 25,000 by 1,500 indicators, so reasonably large. Now, convergence time here is on a log axis in seconds, and this is log predictive likelihood. Again, higher is better. Okay, so that's just one thread of interesting current research, is taking existing models and thinking about ways of making inference much more scalable so we can apply them to very big data problems. Okay? And for Bayesian non-parametrics, this is quite challenging because the models involve data structures that grow over time. So you need to be a little bit careful that, you know, when you give it a huge data set, your algorithm doesn't get slower and slower and slower. Okay? So let's talk a little bit about networks. So a lot of people are interested in modeling networks. And you know, some examples of interesting kinds of networks are biological networks, like this protein-protein interaction network shown here, or social networks, for example, friendship networks, co-authorship networks, etc. Now, what we'd like to have is models that are able to predict missing links in a network, to infer hidden or latent properties or classes of the objects, and to generalize things that you learn from a small network to a larger network. Okay, so we want somehow the parameters that we learn to be sensible when we generalize it to larger networks. So what do I mean by a network? Well, a network has a set of entities and has a set of pairwise relations. So network modeling is actually quite closely related to relational modeling. In fact, it is a form of relational modeling. And these pairwise relations are going to be represented as links or edges between nodes in a graph. Okay? And we can represent this as a binary adjacency matrix where Yij equals 1 represents a link between nodes I and j. And we're going to focus on undirected graphs because it's a little bit easier to think about them notationally. But much of what I'm going to talk about is generalizable to more general discrete graphs. Okay. So I'm interested in modeling networks. What do I mean by a model? Well, a lot of people have done a lot of work on descriptive statistics of networks, but I really want a probabilistic generative model. I want something that can generate networks at random and that I can condition on data, so I can say, conditional on this data, generate me more links or more nodes or whatever. Okay. Here's a very simple probabilistic model of networks called the Erdos-Renyi model. And this model just says there is some probability pi, which is the same for all pairs of nodes, of a link between those nodes. So Yij is a Bernoulli random variable with parameter pi. This is very widely studied, but it's not very interesting as a model because the only thing you can learn about the network is the average density of the network. Here is a much more interesting model of networks. This is called the latent class model. And the basic idea is that it says that the structure of the network arises from some latent or hidden variables associated with each node. So in fact, we can think of a latent class model as having a single discrete hidden variable. And I've shown that by these colored letters here. So node 3 belongs to latent class A, or cluster A. So really, this corresponds to a clustering of the nodes, shown by the colors, which can also be thought of in the network modeling language as doing community detection. So for example, you know, maybe the nodes are people and the clusters correspond to, you know, political views of individuals in a social network, and maybe the friendship relations depend on the political views of different people, or something like that. Okay, so form of the latent class model is given by this classic stochastic block model by Nowicki and Snyders. And essentially, just to describe this in a little more detail, the latent class of node I is drawn from a discrete distribution with parameters p1 through pk. You have k different latent classes. And then the probability of an edge between a pair of nodes depends on the class of node I and node j, okay, through some matrix of parameters. Now, what do you do? I said, I'm interested in models that can generalize to larger networks. So what happens if I add a node to the network? Well, which class should we assign it to? I mean, in theory, we could assign it to one of our existing 4 classes, or maybe we could assign it to a new class. This is a very natural way of motivating a non-parametric model. So we want network models that allow new nodes to belong to new classes. So we want the number of observed classes to grow with the number of nodes. And an example of this is a model called the infinite relational model by Kemp et al. And this model is a generalization of the Nowicki and Snyder's model, a very straightforward generalization. But all it does is it says that the number of latent classes is infinite instead of k. And the assignment of these latent classes follows the Chinese restaurant process. And everything else about the model is the same. It turns out that MCMC in this model is very straightforward to implement. And so it's quite easy to do learning of this model. And it'll automatically tell you the number of clusters or the number of communities in the network.
I have a question.
Yes?
If two objects arrive at the same moment, do we assign them to the one class, let's call it unknown, class of unknown or unobserved objects, or do we assign each of these objects to a separate class?
That's a very good question. So although I described this sequentially by saying that the Chinese restaurant process has people arriving sequentially at the tables, and imagine the nodes arriving sequentially, actually these models have no element of time in them. So the distribution defined over the clusterings, if I show you this picture and I say this is the clustering, there is no way you could know which node arrived first. So the numbering of the nodes is irrelevant. So the fact that I called that node 10 doesn't mean anything. That could have been node 1. Okay? So this is a property I'm going to talk about a little bit. Again, it's called exchangeability. These models are exchangeable in the identities of the nodes, which means that the probability distribution is invariant to any reordering of the nodes, any permutation of the nodes. So there's no order actually here. So I don't know if that answered your question, but it sort of suggests that the assumption is the assumption of some temporal order is not captured by these models at all. Now you can have time series models for networks, and that's an interesting area of research, where you do care about the timestamp of people entering a social network, for example. Okay. Now, infinite relational models are a very, very interesting model, but again, they're following this kind of clustering assumption, which says that every node belongs to only one cluster or one community. And we really want generalizations of this that capture a more rich hidden structure. So these are these latent feature models. In a latent feature model, each node possesses some number of latent features. So here shown by A, B, D, A, C, etc. So node 8 possesses 2 latent features, features A and features C. And alternatively, we can think of this as overlapping clusters or communities. So there is a community A, and there is a community B, and these communities overlap. There's some members that are both in community A and community B. Okay? And we want these latent feature models so that the number of communities is not limited. Okay, so that essentially we have an unbounded number of communities with an unbounded number of nodes. And this is, again, a nice application. Instead of the Chinese restaurant process, this is a nice application of the Indian buffet process to networks. So this was done by Miller et al. In 2010. Miller, Griffiths, and Jordan. And the idea was let Zik denote whether node I has feature K or belongs to community K. and this matrix Z is drawn from an Indian buffet process. And then there's some other part of the model that tells you what is the probability of a link between nodes I and J given the parameters of the model. So again, I won't go into all the details, but just to emphasize the overlapping community structure and this IBP matrix in here. So here is a further generalization of these models called the infinite latent attribute model, which uses both the Indian buffet process and the Chinese restaurant process to model these networks. And basically the idea here is that each object has some number of latent attributes, and each attribute can have some number of discrete values. And the probability of a link between a pair of nodes depends on both the attributes and values of the objects through some link that I'm not going to describe. So the way to think about it is, people might have different attributes, and these attributes might have different values. And then you look up the combination of attributes and values of two different people. This is, for example, at a university like Cambridge, people belong to different colleges, and they might play different sports, etc. Then the probability of a link depends on these attributes and values. Okay, so here is a comparison of the prediction performance for this infinite relational model, the latent feature relational model with overlapping communities, and this infinite latent attribute model I've just described. And the interesting thing is that all three of these models are non-parametric models for networks. But when you look at their predictive performance, it turns out that the more complicated model, the one that can do both aspects of the Indian buffet process and aspects of the Chinese restaurant process, has better predictive performance than the infinite relational model and the other model. So adding more structure to the hidden variables can sometimes be helpful. So I'm pretty much out of time. Let me see. I have some discussion of exchangeability, which I think might be interesting. And I have just some concluding remarks on covariance, modeling covariances. So I think I can cover it in 5 minutes if you're willing to bear with me for 5 minutes. Okay? And I'll look at my watch to make sure I can do that in 5 minutes. Okay, sorry about that. So almost on time. But okay. So exchangeability is a very important concept. An exchangeable sequence is a sequence where the distribution is invariant to permutations of the elements. Okay? And it's a very fundamental concept in Bayesian statistics because there is an important result called Definetti's theorem from the 1930s, which says that if your data is exchangeable, then there exists some random probability distribution, theta, such that your data is IID given theta. So all exchangeable sequences are Bayesian mixtures of IID data. And that's a very important result that motivates Bayesian non-parametric modeling. Now, there is a generalization of that to arrays, where you say that an array, like a matrix, is exchangeable if it's equal in distribution to permutations of the rows and columns. In other words, the ordering of the rows and the columns doesn't matter in the matrix. Okay? So a lot of typical examples of data used in machine learning correspond to exchangeable arrays. For example, data for recommender systems, where you have people rating movies. That's an exchangeable array because you could permute the order of the people and you could permute the identities of the movies, and it's still the same data set. So you still want to have the same distribution on that. There is a theorem called the Aldous-Hoover theorem, which is a generalization of Definetti's theorem for exchangeable arrays. And I won't go into the details of that, but we have a paper where we try to explain this intuitively. So the intuition is that any model of matrices, arrays, or graphs where the order of the rows and columns is irrelevant can be expressed by assuming some latent variables associated with each row and column and a random function mapping these latent variables to observations. So the very recent work that we did at NIPS last year was to take this Aldous-Hoover representation and develop a model for arrays and networks that literally uses this representation. So we say every node is represented in terms of some hidden variables. We can draw those from a uniform distribution. And this random function in the Aldous-Hoover representation, we're going to draw that from a Gaussian process. We're going to say our prior on the random function is a Gaussian process, and we have some latent embedding of the points here. So this ends up being what we call this the random function model for networks, arrays, and relational data. And it turns out that a lot of different models can be thought of as particular forms of this sort of random function model, things like the GPLVM, PCA factor analysis, etc. When we use this model to model networks, we get some interesting properties coming out. We get some interpretability in the results. And also, it tends to give better performance, at least on the data sets that we tried, than other competing models for these networks. And part of the reason for that is that it's a very flexible model. Like, it can really capture properties of a lot of previously proposed models for networks and arrays. Okay. So this is exciting to us, and we're still working on this. This is some of our own very, very recent research. Another area that's interesting is modeling covariance matrices. This is of interest to people, for example, in econometrics. So covariance matrix has to be positive, definite, and symmetric. And so now we can think about, well, what are distributions on symmetric, positive, definite matrices? What are distributions on functions that can take values that are symmetric and positive, definite? And the work that we've done in that area over the last couple of years with Andrew Wilson involves taking a Wishart distribution, which is a distribution over symmetric, positive, definite matrices, and generalizing it to a process, which we call the Wishart process. Okay? It ends up being very simple. All we do is we use this building block, the Gaussian process again, and we can take draws from a Gaussian process, take the outer product of these draws from a Gaussian process, and get a draw from a Wishart process. Just like you can get draws from a Wishart distribution by outer products of Gaussian draws. And again, we can apply this to lots of different kinds of data. So this is just the summary of these last two lectures on Bayesian non-parametrics. And I've now tried to cover quite a lot of other advanced topics in Bayesian non-parametric modeling, including network models, exchangeable arrays, covariance models. I talked about hierarchical clustering, but not kind of all the work that we've been doing there either. But the basic take-home message is really that there are important building blocks. And if you really understand these building blocks, you can put them together to develop models of all kinds of interesting data. And then obviously, ultimately, that's what we're interested in for machine learning, is models of data that we can apply to challenging problems. Okay, so finally, I just want to make sure I thank a lot of my recent co-authors, at least on some of this work. And I've already thanked some of them before, like Andrew Wilson and so on. So the list is incomplete, certainly. And this is a review article that that covers a lot of the material I've talked about in detail. Okay, so I think that was 5 minutes, so I'll end there. Okay.